Imagine holding a small metal marble in the palm of your hand, completely calm and still. Now imagine that tiny marble suddenly swelling up until it swallows your entire room, your street, and your whole town in less than 20 minutes. That exact kind of impossible violent growth is happening at this very second on the surface of our sun. Massive invisible magnetic knots are tearing open, and cosmic storms larger than entire planets are preparing to fire directly into deep space. If you love exploring the raw, unfiltered secrets of our universe without any scientific fluff, make sure you hit that subscribe button right now. We track the wildest cosmic events and break down real discoveries in simple ways every single week. So joining us means you will never miss what is secretly unfolding above our heads. To understand why these cosmic eruptions are so terrifying, we have to look back at how our ancestors saw the sun. For thousands of years, people looked up at the sky and assumed the sun was a solid, perfect, glowing ball of quiet light. Ancient observers believed it sat in the heavens like a peaceful golden lamp, never changing, never angry, and always shining with steady warmth across the blue sky. It was not until the early 1600s, when early astronomers like Galileo Galilei pointed crude glass telescopes toward the light, that humanity realized something strange was happening. Galileo noticed dark, moving blemishes floating across the sun's golden surface, and he could not explain what they were. The scientific world at the time argued fiercely about these dark patches, with many claiming they were simply undiscovered planets passing in front of the blinding solar disk. Today, we know those dark patches are called sunspots, and they are not calm shadows at all. They are giant, churning whirlpools where the sun's internal magnetic fields become tangled, like thousands of thick rubber bands twisted way too tight. Because these magnetic forces are so intense, they block the sun's heat from bubbling up from underneath, making these spots several thousand degrees cooler than the rest of the solar surface. Even though they look black against the blazing light of the sun, a single average sunspot shines brighter than the full moon in our night sky. What makes them so alarming today is that the sun is not a peaceful star, but rather a roiling ocean of superheated, electrically charged gas called plasma. As this liquid-like fire spins faster at its equator than at its poles, the magnetic lines inside get dragged, stretched, and violently warped until they can no longer hold their shape. Every 11 years, our sun goes through a natural wild cycle where its magnetic poles flip completely upside down, turning north into south and south into north. During the peak of this cycle, known to researchers as solar maximum, the sun becomes covered in dozens of these massive dark blemishes. For decades, solar scientists believed these cycles followed a predictable, polite rhythm that was easy to forecast years in advance with simple math. They built complex computer simulations and calculated mathematical models to predict exactly how strong each new storm season would become. But over the last few years, the sun has completely shattered those safe expectations, behaving in ways that have caught the world's top space physicists totally off guard. Instead of a mild, sleepy cycle, our host star has suddenly awakened with a level of explosive fury that experts did not anticipate seeing for decades. Take a moment and ask yourself, have you noticed how wild and unpredictable our space weather reports have become recently? Leave a quick comment below if you have ever seen strange northern lights where you live. Be sure to tap the like button if you want more people to understand the real power of our sun. When researchers at major space organizations like NASA and NOAA looked at their long-term forecasts back in 2019, they predicted the current cycle would be very quiet. They officially announced that this cycle, known as Solar Cycle 25, would be one of the weakest solar periods recorded in the last century. They thought the sun would produce only a tiny handful of minor eruptions, meaning our high-tech world would sit safely out of harm's way for years to come. What actually happened in the real universe was the exact opposite of those calm official forecasts. From the moment the new cycle began ramping up, sunspot counts blew past every single mathematical prediction by huge margins, sometimes doubling the numbers on the charts. Huge active regions, some spanning over 100,000 miles across, began bubbling up on the solar surface one after another like boiling water in an overheated pot. To put that size into perspective, you could drop 12 Earths side by side across just one of these twisted dark regions, and they would still not touch the edges. When magnetic lines of that gargantuan scale snap and reconnect, they unleash a blast known as a solar flare. These flares release the same amount of pure destructive energy as billions of megatons of atomic explosives going off at the very same microsecond. Yet a solar flare is only the first part of the double punch our star can throw across the solar system. Right behind that burst of blinding light often comes something far more massive called a coronal mass ejection, or a CME for short. A coronal mass ejection is essentially a colossal, superheated tsunami made of billions of tons of solar matter hurled outward into the vacuum of space at millions of miles per hour. When scientists watch these CMEs lift off through instruments on space probes, it looks like a giant, glowing cloud tearing itself free from the star's outer atmosphere. These plasma clouds do not simply drift into space like gentle fog. They travel as a dense, electrified shock wave carrying its own powerful magnetic field. If one of these monstrous clouds happens to be aimed directly along Earth's orbital path, our entire planet is forced to brace for impact. Before we look at the next terrifying detail, pay close attention to what happens when this cosmic material finally reaches our world, because it changes everything we know about safety. Our planet is protected from normal space radiation by a giant invisible shield called the magnetosphere, created by the churning molten iron deep inside Earth's core. When a mild solar wind hits this shield, the lines of magnetic force guide the charged particles toward the north and south poles, creating the beautiful, dancing sheets of light we call auroras. For thousands of years, humans stood on snowy hills and watched these silent glowing curtains in total awe, never realizing they were looking at the debris of a distant solar war. For a long time, the general public believed that these space storms were completely harmless to anything sitting on the ground beneath our thick blanket of air. Most people still assume that because our atmosphere blocks harmful X-rays, solar eruptions are nothing more than a pretty light show in the northern sky. But the reality of our modern, hyper-connected world makes this old assumption dangerously outdated and completely false. While the physical air keeps human lungs safe from breathing space plasma, the invisible electrical shock wave from a giant storm does something far more insidious. As billions of tons of magnetic plasma slam into Earth's protective bubble, they compress and warp our planet's magnetic field lines like a giant squished balloon. This rapid warping creates massive phantom electrical currents that surge directly into the ground and crawl up into our metal infrastructure. These rogue currents do not care about electrical safety switches or standard power grid protections built by utility companies. They force their way directly into the massive high-voltage transformers that keep our cities powered, our hospitals running, and our water flowing. Because these giant transformers are designed only to handle smooth, alternating current, the raw, direct current, from space heats their giant copper coils until they literally boil their own cooling oil and explode. Think about how much you rely on electricity every single hour of the day, from your phone battery to the water coming out of your sink. Did you realize a blast from 93 million miles away could melt a metal power station right here on the ground? If that fact surprised you, hit the subscribe button and join our growing community of curious minds uncovering the deepest secrets of our living universe. To see what happens when the sun truly decides to let loose, we have to look back at a famous date in modern history. September 1st, 1859. On that clear morning, a British astronomer named Richard Carrington was sitting in his private observatory sketching a gigantic group of sunspots on a piece of paper. Suddenly, right before his eyes, two blinding patches of intense white light erupted directly above the dark spots and vanished within 5 minutes. Carrington had just witnessed the first recorded supersolar flare in human history, and what followed 18 hours later shook the entire globe. The resulting coronal mass ejection hit Earth with such incredible velocity that the night sky across the planet lit up as bright as noonday. In places like the Rocky Mountains, gold miners woke up in the middle of the night, thinking the morning sun had risen, and began cooking breakfast over their campfires. People in tropical places like Hawaii, Cuba, and southern China stepped out of their homes and saw vivid red and green lights dancing over the ocean. But the most shocking damage happened along the only advanced technology that humanity possessed at the time, the global telegraph network. Thousands of miles of copper telegraph wires suddenly began absorbing the violent geomagnetic currents flowing through the dirt beneath them. Telegraph stations caught fire as sparks showered out of the metal transmitters, burning the hands of operators who tried to touch the keys. In several locations, workers completely disconnected the heavy batteries. Yet the telegraph machines continued sending messages across hundreds of miles powered entirely by the electricity surging through the sky. If an identical Carrington-level event were to hit our planet today, the consequences would be thousands of times more catastrophic. Back in 1859, humanity did not rely on satellite communication, GPS navigation, digital banking, or interconnected continental power networks. Today, our entire global civilization depends on a fragile spiderweb of delicate electronics that has never experienced a direct hit from a Category 5 solar superstorm. If one strikes without adequate warning, thousands of giant transformers across multiple continents could melt simultaneously, leaving entire nations without electrical power for months or even years. Replacing a single one of these giant multi-ton transformers is not as simple as buying a spare part from a local warehouse. They are custom-built, weigh as much as several large elephants, cost millions of dollars, and often take over a year to manufacture and deliver using specialized transport trains. If dozens of them burn out in a single afternoon, there are simply no backup units sitting in storage to restore power to hundreds of millions of people. Listen closely to this next reality. Because scientists have just discovered something about the sun's current behavior that makes the threat immediate. We are not just talking about distant history. The sun has entered an unusually erratic and volatile phase right now. Modern satellites like NASA's Solar Dynamics Observatory and the European Space Agency's Solar Orbiter are currently recording dozens of powerful solar flares every single month. Some of these active regions are firing off what scientists classify as X-class flares, the most potent category of explosion our star can produce. An X-class flare is not just a little larger than average. The scale works like an earthquake scale, where an X10 flare is 10 times more powerful than an X1. In recent months, astronomers watched an active region named AR3664 grow into a sprawling magnetic monster so massive it rivaled the famous Carrington sunspot of 1859. This single gigantic scar on the sun unleashed a relentless barrage of megaflares and fired multiple overlapping plasma clouds directly into interplanetary space. When those overlapping clouds slammed into Earth in May of 2024, they generated the strongest geomagnetic storm our planet had felt in over 2 decades. Auroras were visible as far south as the Caribbean, while farmers in the Midwest watched their precision GPS tractors suddenly steer off course in the middle of their fields. Deep ocean sensors, thousands of feet beneath the Pacific waterline, even recorded the magnetic shift rippling through the planet's crust. What makes these storms even more dangerous is a phenomenon known as cannibal coronal mass ejections. This happens when an active sunspot fires off one plasma cloud, and then a few hours later fires a second, much faster cloud in the exact same direction. The second, faster cloud sweeps through space like a cosmic snowplow, gobbling up the first cloud and combining their magnetic fields into a single, hyper-compressed wall of destruction. When a cannibal storm hits Earth, it does not just rattle our magnetic defenses. It violently cracks them wide open, allowing massive amounts of radiation to pour into our upper atmosphere. This radiation heats the thin gases of the upper atmosphere, causing the entire outer air blanket of our planet to expand outward like a baking loaf of bread. As the atmosphere swells upward into the orbital paths of human satellites, it creates an invisible wall of heavy air drag. Have you ever thought about how fragile our space satellites really are as they race around our planet at 17,000 miles per hour? If you find it fascinating how a storm on a star can literally drag metal machines out of orbit, drop a comment below telling us what you think engineers should do to protect them, and hit that like button to support real science deep dives. When the upper atmosphere expands from solar heating, satellites in low Earth orbit are suddenly forced to fly through thick, dragging air instead of empty vacuum. This unexpected friction slows the spacecraft down, causing their orbital altitudes to decay rapidly toward the ground. In early 2022, a single moderate solar storm caused the loss of nearly 40 brand new internet satellites in a single day, because the air swelled up before ground controllers could boost them to safety. Beyond low Earth orbit, out at 22,000 miles where our weather and communications satellites hover, the danger is just as severe. These expensive spacecraft sit directly in the firing line of what scientists call killer electrons, high-energy particles energized by the solar storm. These particles act like microscopic bullets that drill directly into sensitive computer chips, scrambling satellite memory banks and blinding their solar panels permanently. For the human beings currently living and working aboard the International Space Station, a major solar eruption is a matter of immediate life and death. Because the space station orbits within Earth's inner magnetic field, the astronauts receive some natural protection. But during an extreme storm, radiation levels spike to dangerous highs. When massive solar proton storms erupt, astronauts are ordered to retreat into the most heavily shielded modules of the station, surrounding themselves with thick water tanks and dense cargo bags to absorb the invisible atomic hail. If an astronaut were caught outside on a spacewalk during a major solar proton event, they would receive a lethal dose of radiation within a matter of minutes. This reality presents a gigantic hurdle for future space missions, aiming to build permanent bases on the Moon or travel outward to Mars. Out in deep space, completely beyond the protective umbrella of Earth's magnetic core, human travelers have zero natural shield against the violent whims of our host star. What makes this puzzle even more baffling to modern astronomers is that the sun does not always give clear warning signs before it unleashes a catastrophic blast. For many years, scientists believed that every massive solar storm was preceded by hours of slow, detectable swelling in the local magnetic field. They thought we would always have a comfortable multi-day warning window to power down electrical grids and put satellites into safe modes before the shockwave arrived. Yet recent satellite observations have documented stealth coronal mass ejections, which erupt from quiet, unassuming regions of the sun without any bright flare or obvious surface warning. These stealth storms slip away from the star unnoticed by automated tracking systems, drifting silently through the blackness of space like invisible naval mines. Earth can find itself slammed by a severe geomagnetic disturbance before ground-based space weather forecasters even realize an eruption has taken place. Here is the critical twist that researchers are only now beginning to fully understand. and it changes how we view our entire modern timeline. Scientists have recently turned to ancient history to figure out just how powerful our star can truly become when it reaches its absolute limits. They started drilling deep ice cores out of the frozen sheets of Greenland and Antarctica, pulling up ancient layers of snow that fell thousands of years ago. By analyzing the tiny chemical isotopes trapped inside those ice layers, specifically an isotope known as beryllium-10, they discovered evidence of solar events that make the Carrington Event look like a tiny spark. They also examined the ancient growth rings of thousand-year-old cedar and pine trees preserved in riverbeds and old forests around the world. In the wood grown in the year 774 AD, researchers led by Japanese physicist Fusa Miyake discovered an immense, terrifying spike in radioactive carbon-14. This massive spike, now known as a Miyake Event, proved that our sun once unleashed a radiation storm dozens of times stronger than anything humanity has witnessed in modern times. If a Miyake-level superstorm were to strike our planet tomorrow, the damage would not just be blown transformers and flickering light bulbs in a few major cities. The intense wave of solar protons would trigger chemical reactions in our upper atmosphere that would severely deplete the protective ozone layer for several years. This loss of ozone would allow dangerous ultraviolet radiation from the sun to pour down onto the surface, harming crops, damaging marine food chains, and increasing skin cancer rates across the globe. It would also permanently fry the internal circuitry of nearly every satellite orbiting our world, instantly blinding global navigation, military surveillance, and international communication networks. Commercial airliners would lose all satellite positioning mid-flight, shipping vessels across the oceans would be rendered blind, and global supply chains would grind to an immediate, catastrophic halt. The economic cost of such an event has been calculated by risk analysts to reach tens of trillions of dollars in the first year alone. Consider this. Our modern world is entirely built on an invisible foundation of electricity, microchips, and space signals that did not exist during the last great solar superstorm. Are we truly ready as a society to survive a month without the internet, clean tap water, or working supply lines? Share this story with someone who loves mind-bending space science, and tap subscribe right now so you never miss another deep look into the real forces shaping our universe. To understand why our modern world is so uniquely vulnerable, we need to trace the journey of an electrical current through a modern city during a solar crisis. When the sun launches a coronal mass ejection toward Earth, the energetic particles travel across 93 million miles of empty space at breathtaking speeds. When this charged plasma collides with the magnetosphere, it squashes Earth's magnetic bubble on the sunward side, while stretching it into a long, trailing tail on the night side. This stretching action stores an immense amount of magnetic energy in Earth's immediate space environment, much like pulling back a giant slingshot. When that stretched tail finally snaps back toward Earth in an event called magnetic reconnection, it fires billions of watts of electrical energy down into the upper atmosphere. This atmospheric electrical surge creates what scientists call geomagnetically induced currents, which look for the easiest metal pathways into the ground. High-voltage transmission lines act like giant metal antennas that greedily absorb these wandering ground currents across hundreds of miles of open countryside. Because the wires are connected to grounded transformers, the extra current flows directly into the core of the power stations. The iron cores inside these transformers quickly become oversaturated with magnetic energy, which causes them to vibrate wildly and produce a terrifying, low-pitched buzzing roar. As the transformers hum violently, their internal temperatures spike to hundreds of degrees in just a few minutes, turning cooling oil into flammable vapor. In 1989, a relatively moderate solar storm triggered this exact chain of events across the Canadian province of Quebec. In less than 2 minutes, the entire electrical grid of Quebec collapsed, plunging 6 million people into freezing darkness for over 9 hours while power stations burned. If a storm 10 or 20 times more energetic were to strike during the coldest days of winter, the collapse would not be limited to a single province. Entire continental power grids in North America, Europe, and Asia could trip offline within seconds as automatic safety breakers fail to stop the cascading overload. Without power, water treatment plants cannot pump clean drinking water to homes, wastewater systems back up into streets, and refrigerated food warehouses spoil within 48 hours. Gas stations rely on electric pumps to dispense fuel from underground tanks, meaning emergency vehicles, food delivery trucks, and repair crews would quickly run out of fuel. Modern hospitals have emergency diesel generators, but those backup generators typically carry only enough fuel to run critical life support machines for a few days. Without a functioning fuel supply chain to deliver fresh diesel, even the most advanced medical centers would eventually go completely dark. Can you imagine waking up tomorrow morning to find your smartphone showing zero signal, your light switches completely dead, and no water flowing from your faucet? Tell us in the comments what the very first thing you would do in that situation is, and make sure to subscribe so you can keep learning how our planet interacts with deep space. The danger reaches far beyond land-based power grids and threatens the hidden backbone of global communication: undersea internet cables. Stretched across the rocky floors of the Atlantic and Pacific Oceans are hundreds of thousands of miles of fiber optic cables that carry nearly all international internet traffic. While the glass fibers inside these cables transmit harmless light pulses, the cables also carry long copper power lines to feed electrical repeaters spaced every 50 miles apart. These long underwater copper lines are just as vulnerable to geomagnetically induced currents as overhead power lines on land. A massive solar storm could induce strong electrical currents along the ocean floor, burning out the underwater repeaters and severing the physical internet links between continents. Such a breakdown would cause what computer scientists call an internet apocalypse, cutting off cross-border banking, trade, and communication for weeks at a time. Aviation safety is another critical area where solar storms pose an immediate and invisible threat to thousands of daily travelers. When planes fly across high northern latitudes near the North Pole, they leave the coverage area of standard ground radar and rely entirely on high-frequency radio signals to communicate with air traffic controllers. During severe solar proton events, the upper polar atmosphere becomes completely ionized, absorbing high-frequency radio waves and causing sudden polar radio blackouts. When pilots lose radio contact over the icy Arctic, they are flying blind without voice communication or real-time space weather updates from ground stations. At the same time, high-altitude radiation exposure increases dramatically for everyone on board, exposing flight crews and passengers to radiation doses equivalent to multiple chest X-rays in a single flight. To prevent these risks, airlines are forced to divert dozens of long-haul flights to longer, lower-latitude routes, burning millions of gallons of extra fuel and causing massive travel delays. Underwater submarines, military defense radars, and precision agriculture equipment are also disrupted by rapid fluctuations in the ionosphere. Modern farming equipment uses satellite signals to steer heavy tractors within an accuracy of a single inch to plant seeds and apply fertilizer efficiently. During geomagnetic storms, the distorted signals create positioning errors of several feet, forcing automated farming machinery to shut down completely to avoid damaging crops. Even the animal kingdom feels the confusing effects of our sun's violent magnetic outbursts across the globe. Many migratory animals, including songbirds, sea turtles, homing pigeons, and whales, possess a biological compass that allows them to navigate using Earth's magnetic field lines. When a solar storm violently bends and distorts those magnetic lines, migratory birds can lose their way along ancient flight paths, and pods of whales have been known to strand themselves on sandy beaches. Have you ever wondered if the wild animals around your neighborhood behave strangely when space weather warnings are active? Share your observations in the comments below, and give this video a thumbs up if you find it amazing how star storms touch every corner of life on Earth. To fully understand why these solar explosions happen in the first place, we have to travel straight into the boiling heart of the sun itself. Deep inside the solar core, temperatures reach over 27 million degrees Fahrenheit, creating pressure so extreme that hydrogen atoms are constantly fused into helium. This continuous nuclear reaction creates pure energy that takes over 100,000 years to slowly crawl its way out to the visible surface. As that intense energy nears the outer layer of the star, it moves through a boiling convective zone that works just like a giant pot of thick soup on a roaring stove. Columns of superheated plasma rise to the surface, cool down slightly, and then sink back down toward the core to be heated all over again. This endless churning motion turns the sun into a giant natural dynamo, generating massive magnetic fields that twist around the star like an enormous cage of live electrical wires. Because the sun is a giant ball of fluid gas, rather than a solid rock like Earth, different parts of the star rotate at completely different speeds. The equator completes a full spin in about 25 days, while the polar regions take up to 35 days to make the same full turn. This uneven rotation slowly stretches the magnetic field lines, pulling them sideways and winding them tighter with every single passing week. Eventually, these stretched magnetic lines become so tangled and twisted that they form dense rope-like knots beneath the solar surface. When these magnetic ropes become too buoyant to stay submerged, they punch upward through the glowing photosphere, forming pairs of dark sunspots connected by towering magnetic arches. These magnetic arches, known as coronal loops, can rise hundreds of thousands of miles into the sun's outer atmosphere, glowing brightly in ultraviolet light. As more magnetic ropes rise and tangle with existing loops, the tension in the solar atmosphere builds to a critical breaking point. When two oppositely charged magnetic loops are forced together by the boiling motions beneath them, they suddenly snap and reconnect in an explosive flash. In that tiny fraction of a second, the magnetic field reorganizes itself into a simpler shape, releasing all its stored tension as blinding light, energetic particles, and billions of tons of ejected plasma. What makes this process even more fascinating to physicists is that we still cannot predict the exact second when a magnetic knot will snap. We can watch a sunspot grow, measure its magnetic complexity, and calculate the probability of a flare, but the actual trigger happens at microscopic scales hidden deep within the plasma. This means that even with our most advanced space telescopes constantly staring at the sun, a planet-sized explosion can erupt without a single second of advance notice. Despite these terrifying possibilities, our understanding of space weather is improving at a faster rate than at any point in human history. Scientists and engineers are building an advanced early warning defense network spread across our solar system to give humanity precious time to react. Probes like the Parker Solar Probe are currently flying directly through the blazing outer corona of the sun, skimming just millions of miles from the fiery surface to taste the magnetic storms right where they are born. By measuring the exact speed, temperature, and magnetic orientation of the plasma at the point of origin, these probes are helping scientists build better predictive computer models. If space weather forecasters can determine the magnetic polarity of an incoming storm while it is still racing toward us, they can tell whether it will harmlessly bounce off Earth's shield or latch onto our magnetic lines and rip them open. A warning window of even 12 to 24 hours would allow power company operators to safely disconnect vulnerable transformers and route power through backup systems before the rogue currents hit the ground. Satellite operators could rotate expensive spacecraft so their most heavily shielded components take the brunt of the radiation blast, protecting their delicate electronics from permanent burnout. Commercial airlines could reroute long-distance flights away from polar routes, where radiation exposure and radio blackouts are most severe, keeping passengers and crew members safe. Even astronauts on future lunar missions could use these warnings to duck into buried underground lava tubes beneath the moon's dusty crust until the radioactive storm passes. Engineers around the world are also developing new hardware solutions to harden our vulnerable electrical infrastructure against space weather. Grounding capacitors and neutral current blockers are being installed at critical power substations to stop geomagnetically induced currents from entering transformer cores in the first place. These specialized blockers act like heavy-duty one-way valves, allowing normal alternating current to flow safely while slamming the door shut on dangerous direct current rushing in from the dirt. Meanwhile, space agencies are working on deploying replacement satellite constellations designed with radiation-hardened microchips that can withstand extreme particle bombardment without crashing. By distributing critical tasks across thousands of smaller, cheaper satellites, rather than relying on a few massive, expensive spacecraft, our global communication network becomes far more resilient to sudden space weather losses. If a solar flare knocks out a handful of small satellites, the remaining network can automatically reroute signals to keep global communications alive. The sun is not an evil villain trying to destroy us, nor is it a cold, unchanging light bulb hanging in the empty sky. It is a dynamic, living, magnetic engine that gave birth to all life on Earth, providing the light, warmth, and energy that allows our civilization to exist in the first place. But like any immense cosmic force, its power comes with an inherent volatility that demands our deepest respect, continuous study, and serious preparation. Every time you look up at the bright sky on a warm afternoon, you're gazing at an active nuclear reactor containing over 300,000 times the mass of our entire planet. It is constantly churning, twisting, and building up invisible forces that dwarf the entire energy output of human civilization by billions of times over. The storms are brewing right now, their magnetic triggers are tightening by the day, and our planet sits directly in the cosmic arena where those forces will eventually play out. We are living through one of the most active and surprising solar periods in recorded history, and the next few years will test our modern technology in ways we have never experienced before. How do you think our global society should prepare for the next inevitable superstorm? Drop a comment down below with your thoughts on whether we are ready for a major space weather blackout. Hit the subscribe button, turn on all notifications so you catch our next deep dive the moment it drops, and share this story with your friends and family. Thank you so much for watching, and stay curious until next time.